Okay, so good evening, everyone. We'll resume discussion about convolutional neural networks, and then talk about a couple of new topics. So I'm just continuing with the last lecture slides, and then I think the new lecture slides are also available online. So we'll get to that pretty soon. So last time, several of you got confused with this diagram. It's actually a animation. So let me open that animation. This one. So those of you who understand what's happening, it's fine. But basically, this yellow, my 3x3 grid is the filter. Okay. Just think of no depth for now. So let's just say this is an image, no RGBs, just a grayscale thing with zeros and ones representing black and white. Okay. So you're basically so the filter depth has to be the same as the input depth. So input image is depth 1, in the sense it's a matrix. If there were depth 2, maybe it's a tensor with third dimension being 2, right? So the convolution operation is essentially an element-wise multiplication of a matrix with another matrix. So it's basically the red numbers are the second matrix, and the original numbers are in the green. And so basically you do element-wise element multiplication, add them up, and that's the number 4 over there. And you just keep moving, left and right, and maybe down, and then you get these numbers. Okay. So this is what is the first view, which is the filter view. So a filter is just represented as a matrix here, and the filter view is just saying that you get some output, right? If input is just a matrix, I'm going to slide my filter, which is again actually just a matrix here, over my input matrix and get an output matrix. And and it doesn't matter if the filter has depth and the input has depth, you still get a matrix as the output. Okay. If there was depth, if there were 2 green layers, then there will be 2 yellow layers, and they'll all be doing element-wise element multiplication, getting a single number, and that could be over here. Okay. So that's convolution, and it's called convolution because if you flip the matrix in some way, it's a convolution operation, signal processing. But for us, it's not very critical. It's just an element-wise multiplication. Okay. There's a different diagram. This also was a snapshot in the slides, or maybe we'll get to that later on the slides. A couple of slides later. Here it's actually just showing the same thing as before, but now you have 3 matrices stacked together as an input matrix. Okay, sorry, input tensor. So the tensor has 3 layers of 3 matrices stacked on top of each other. There is something, there's gray border around each input matrix of the input tensor. That's called padding. Okay, it's just add some numbers, in fact, add zeros around, as a border for you for the input. That's a design choice. You can add a border of gray, these cells, or you don't. Now, just like we saw in the previous diagram, it was just a 1 matrix as an input, and so filter was also depth 1, so it was only a 3x3 matrix. Here the filter has to be the same depth as the input. So input has 3 matrix slices, is represented by 3 matrix slices. So the filter is also represented by 3 matrix slices. And in this diagram there are 2 filters, so let's not worry about the second filter. Filter W1, filter W0, as I said, is just parameterized by 27 numbers here. Okay, and these are the entries of the filter. So given the entries of the filter, a convolution operation is essentially going left to right, below, and so on, and doing element-wise multiplication, adding. So you multiply this with maybe the top part, multiply this with the top part, multiply this with the top part, add all that up, and you get one number there. Okay. So even though depth is 3, this filter is leading to 1 matrix as the output, and this filter will lead to another matrix. This is this matrix. Okay. So number of filters is number of output depth, okay. And the filter depth itself is going to be the input depth, and you see here there's a slight difference between this sliding of filter versus the previous animation. In the previous animation, the filter was moving 1 step to the right. Here the filter is moving 2 steps to the right. Okay, like it's at the top left, then it's actually moving 2 steps, then coming here, and then moving 2 steps, going there. Okay. It's called a stride, and I'll explain the stride again. Because it's moving 2 steps, you still have an output size which is 3 cross 2. Even in the previous animation, the filter was moving 1 step to the right, and we got a 3 cross matrix. Here we have a 2-step moving. So just to recap, the previous one was moving 1 step. So there was no 0 padding here, there is no 0 scale, right? And the filter is moving 1 step. It's moving 1 step. Okay. So that's the filter view. So basically, if you really want to understand the convolution layer, there are only two perspectives. I mean, you can think of more things, but the first perspective is the filter view, and the second perspective is the neuron view. But the neuron view is not really intuitive, so that's why first I introduced this matrices, or tensors being processed according to filters sliding on top of each layer of that tensor, and then I said they are related to neurons in some way. Yeah. Yeah. So the values of this filter matrix, this 3 cross 3 matrix, are the ones we need to learn. So these are the W parameters. In a feed-forward network, it's clear. There's a one single gigantic W matrix, which has number of rows equal to the number of hidden layers, and number of columns equal to the input size, whatever is the previous layer size or the input size itself. Here, these values are actually same as the weights, so they will be learned. As in, you need to do gradient descent and backprop. Okay. What's the use of padding? What's the use of padding? There is some restriction, right? The question is, if the filter is not being applied, like the center multiplier is not being applied to these entries, so if you want to kind of move to that area. You do this padding tricks with images all the time, not specifically to CNNs. You can do that for regular image processing as well. Yeah, if you choose padding, it will influence. So if you had padding here, then you would have more entries, right? You would have one more entry here and one more entry here. So it would be 5 cross 5. If you had one layer of padding, so this is 5 cross 5 input, right? If I added one layer of padding and then did the same sliding as what this guy is doing, then my output will also be 5 cross 5. Like I'll have one more column here, one more column here, and one more row here, one more row here. So in the second animation, yeah, output is there are 2 filters, so 2 output matrices. Okay.
Yeah, and the first output is corresponding to the first filter.
Yeah, so this block, these 9 numbers correspond to this filter operating on the whole. This whole thing is input now. A lot of numbers, but don't worry about the numbers.
So the first will give you like numbers. The first filter with the first input volume will give you 9 numbers.
So this matrix slice of this first filter, when multiplied element wise, will give you an intermediate number. Second one will also, in the same region, will give you an intermediate number. Third one will also multiply and give an intermediate number. Add those 3 numbers together, and that's one number we will get.
So basically, the red outputs, first, if you see the first element of each of them, the sum of all of them should be the first element of the green matrix, right?
You multiply this whole matrix element-wise with this whole region.
Okay, now got it.
So it's basically 9 numbers multiplied by 9 numbers, 9 with 9, 9 with 9. You get 27 multiplications, 27 intermediate numbers, add them all up, and that's -4. This is just trying to understand the architecture. Maybe you're saying who kind of thought about this architecture? Seems very weird. We'll get to some intuition. So this is related to this parameter count that I was talking about last time, where if you had a fully connected layer, if you had a regular feed-forward neural network, so every neuron in any layer will be connected to everything before it. So if the input is 1000 cross 1000 pixels, then you have 1,000,000 weights for one neuron, okay? And million weights if there is no RGB. If there is 3, then there's 3 million weights per neuron. And if you have 100 neurons in your hidden layer, which is quite small, then you already are like in 300 million type, range. Those many weights, to kind of tune those many weights is kind of really is a bad allocation of parameters. So this is a better allocation of parameters. Yeah.
So would the output change with the padding?
Yeah, of course. I mean, padding is basically you're spuriously introducing some data, right? I mean, so it will of course influence your output. Yeah. But this is a standard image processing trick, so it's
advantage of it, same question.
no, to cover certain regions, right? So you may have a bigger filter. You have 3x3, like let's say you have 10x10 filter. It's not really, and maybe the filter is essentially trying to capture some sort of. Actually, there is some other link as well. One second. Setosa, maybe. Forget that. Yeah.
Padding, you just try design choices, or is it something?
Yeah, design choices. I'm not sure that's not the right word, or maybe it is the. What is the link? Yeah, I guess they took it down. Kernels, KER. Yeah, good point. So this is just a, there is no depth here. So let's say it's a black and white image. So this is a example of a filter. Okay. So think of this 3x3 matrix. This red. This is basically 3x3 matrix. The entries are these: 0, -1, 0, -1, 5, -1, 0, -0. And the cells actually, in a grayscale image like this, can go from 0 to 255. And so here we're just multiplying element wise, right? Getting one number, and that's the output at that location. Okay. So before these types of hand design filters, this is called a sharpen, I guess, filter or kernel. There's something called outline. So you get an outline of, you're basically detecting edges, for example, or things like that. Okay. Outline basically, yeah, everything else around is -1, and the central cell is 8. So anyway, your question is about why we are adding padding, right? So bigger filters require, if you really want to cover certain region, okay, then you want to have some padding so that you can actually detect that feature.
For example, in an image, the more features will be captured with
no, something is at the corner, right? So where is this? Pick any, whatever, not identity, let's say, outline, let's say. So where is this? Okay, here actually they are doing padding, or maybe not, I'm not sure. Yeah, if there is something to detect here, like maybe there's a sharp edge here, unless you go a little bit away, maybe you won't detect that edge. That's right. So you don't have to, if you don't really like the choice, you don't have to put padding.
So kind of
That's going to restrict your, huh?
A better output with padding than without padding.
That's not guaranteed. This is just an engineering choice. Padding may improve your performance of whatever you're doing. Ultimate goal is, or maybe not. Adding padding, I think will it doesn't really cost you more resources, in the sense your parameters are just these filter weights. So whether you added padding or not is not going to influence the number of parameters. You're not increasing the complexity of your model by adding padding, but it's your choice. It's not guaranteed that it's going to really improve performance or anything. Yeah. Where was I? Okay. I don't know if this works. Oh yeah. Okay. Where were we? Yeah, and so this picture is where I think I stopped last time. And this picture is just saying, in this case, the input tensor is 32 times 32 times 3. So it means the input tensor's depth is 3. And let's say the number of filters is 5, which means the output depth is going to be 5. Okay. Output tensor depth is going to be 5. And if there are 5 filters, each filter will produce a matrix, right? Those matrices are what stacked, as this, right? In this case, the filters are all the same size, so you have the same, same sized output. Okay. And now we're gonna kind of now go back to the neuron view and try to understand how filter parameters are related to neurons. Okay. So in this case, you see, I mean, so if you did not think of neurons, all we're doing is putting in one number here, which is the element-wise multiplication of the filter with input values in this area, and computing one number, right? That's what a neuron also does. A neuron, if you remember, a neuron or a node is basically just doing some weights. Okay, let me not use AI. Some weights times inputs, right? So let's say j is equal to 1 to, let's say 27. Okay. So if you remember from feed-forward neural network part of the slides, first a neuron does, neuron basically has a bunch of weights. Whatever input it gets, it's going to do element-wise multiplication, and then it just passes through non-linearity. So this value maybe is z. Then let's say sigmoid non-linearity is 1 by 1 plus e to the power minus z, right? That's it. So this is what neuron does. It just gets some input, it does element-wise multiplication, and passes to non-linearity.
So I just wonder, because the first layer should be like the same size as the input layer, and then the second layer should be smaller, and the third layer should be
doesn't have to be. We just saw if we put padding and do one stride, then the output matrix size is the same as input matrix size. So it doesn't have to like tunnel. I mean, you can always apply.
Since the W is always like more than 1, right? And
yeah, these are 27. If you remember the original, if you look, remember this animation, then it's 27 guys, right? Where is this?
So it's like at the end of maybe the first layer, each neuron should, a result of each neuron should be like 20 or 30 or 40.
No, each neuron just computes one number.
Oh.
Okay. Each neuron just computes one number. So actually, what I'm trying to motivate is that if you think of an output tensor, each cell of that output tensor is a neuron's output, basically. Because each neuron has to output something, and you're stacking these outputs in a nice tensor, as a tensor. So the number of neurons is actually in this layer, in the CONV layer. If it has, let's say, 5 filters here, 5 filters, and the spatial dimension is determined by the filter dimension and input dimension. Then all these are just each cell is actually a neuron computation happening. Okay. We haven't yet tagged on the non-linearity part, because here we are just saying do element-wise multiplication, take an output, but we can always do element-wise non-linearity. I mean, it's basically a bunch of numbers. Each number you just transform by 1 by 1 plus e to the power minus c. That's like a neuron computation, right? I mean, there's also bias that you can add. You can add a plus constant.
Could you go to slide number
62. Okay.
So it says filters are small, long, width and height.
Where does it say that? Filters are small and long width. I mean, yeah. I mean, so if the input image is 1000 cross 1000, I mean, you saw the example, right? In that sharpen filter, it was exactly 3 cross 3. So all these classical image processing. So this is actually classical image processing where they hand engineer a filter with these numbers and call it a particular name. This is called the outline filter. So this is only 3 cross 3 irrespective of the image size. That's all I meant. By small in terms of width and height, it's like it's trying to detect something like an outline, like a line maybe, or a circular pattern or something like that. Okay. Yeah, there's probably a bias here, so let's add a bias, maybe some constant, some other parameter which is fixed, let's say 10 or something. You add 10 to that sum and then do the transformation 1 by 1 plus e to the power minus c. Okay. Yeah, and trying to motivate towards this parameter sharing, or why CNN is better, more efficient in terms of using parameters than fully connected or feed-forward neural networks, is because, like for example, in this case, whatever numbers we compute and do the transformation, these computations only look at a small region. Okay, that's the first point. I mean, that's okay. I mean, they look at a small region. So each neuron is only looking at a small region rather than the full input. Okay, in feed-forward networks, each neuron looks at the whole input. So there's no need for a tensor type of a thinking. I mean, each neuron, you can just tag them as a line, as a one below the other and think of each neuron connected to everything in the input. Okay. Here, each neuron is only connected to a small region. And in fact, each neuron is actually in this whole slice. So this slice, let's say this is the first, I mean maybe not the first slice, but okay, this is some slice. All the neurons use the same weights because all the neurons are basically equivalently, it's the same filter being applied to different regions, right? So all the neurons in this matrix, right, in this slice, are all using the same weights or the same parameters. Okay, so that's the kind of key idea in convolutional neural networks. So is that clear that all the neurons in the same slice are? So you can think of, actually, if you go back to the previous. Okay, where is this? So if you think of this is actually a neuron computation. So what I'm saying is, so in this very simple case, there's only one filter, so the output is not really a tensor, it's a matrix. Think of it that way. And so think of this as a neuron. Now this neuron is only looking at this top part, top 9 cells of the input, okay, and computing a number, and it's going to transform it. This neuron is using the same weights, looking at a different region, computing a number, and eventually it's going to transform it. Here we are not showing the nonlinear transformation. Okay, so all these neurons, in this case 9 neurons, are all using the same weights, okay, which are these red numbers here. So you can imagine the same thing is happening if there is depth in the input, and that means that your filter will also have the same depth, and each filter will generate one such matrix layer. And so you can imagine the other, if there is one more layer at the output, then all the neurons in that layer are also using a small set of weights which correspond to a single filter for computation, right? So yeah. If what has a depth?
If the image has a depth, RGB,
yeah.
Then for a single filter,
yeah.
In a single layer, does the weights change for that filter?
Yeah, of course. So weights are still, weights are essentially parameters, right? W's, and W's are, if you have a parametric model, W's you get to choose what to set them so as to achieve some goal like classification accuracy. So the weights potentially can be arbitrary. So I think in the second animation the weights are not the same, right? I mean. So if you look at these numbers on that side, these numbers are probably not the same, right? The filter entries are not the same. Think of the 3 layers maybe being input RGB if you want, but it doesn't have to be actual input. It can be the previous layer's output. Okay, previous convolution layer's output can be 3-dimensional. I mean 3 in depth, and you can have one more convolution layer afterwards. Okay. Is it? Yeah. Yes, that is precisely. I mean, so these weights are chosen by backpropagation. Here, for example, we are just using simple zeros and ones. And these can be real numbers, and these numbers are set using backprop. So just like neural nets, feed-forward neural networks weights are set by backprop. In fact, we ran a code, which was 2-layer neural net with one hidden layer in between, right? So the weights are set by backprop. And similarly here, these weights are also set by backprop.
So in a single layer, the filter, the weights is different. In a single layer, each neuron will have the same weights. Right?
Single output layer, and when you mean that, I want to be precise. It's this slice here, right? This would be one single layer of the output, right? All the neurons here, maybe 9 neurons, for example, like in the previous animation. All those 9 neurons will have the same weights, so they are only using 27 parameters. If each one had different weights, then it will be 9 times, maybe 27. Maybe if each one is looking at the whole input, then it's 9 times, 3 times 32 times 32, right? Those many numbers. So we've really decreased the number of parameters or numbers, weights that we're using. Okay. Any other question?
How do we determine the filter count? It cannot be determined by backpropagation.
Why cannot it be determined by backpropagation?
Because the size is, different design choice.
Which size?
Filter size, in white filter.
Yeah, we are not choosing filter size of the backprop. You can, it's a discrete quantity, so maybe you don't want to do continuous optimization, but the filter weights themselves are real numbers. The cell entries of those matrix can be real numbers, and then you can do continuous optimization. I mean, you can actually do just the gradient descent. So it's just don't get confused with convolutional networks, right? It's just an arrangement of the neurons. Otherwise, it's the same weights as a feed-forward network. In feed-forward network, there was no structure per layer. You can just stack each neuron below each other and connect it to everything before it. Here, there's a little bit more structure, but it's the same weights at related to every neuron. If neurons are sharing weights, then I don't know if you remember, but there was a slide in the first lecture which was saying weights go to two different neurons, are related to two different neurons, but ultimately lead to a loss function. Then you can backprop and you can add those gradients back. Okay, I don't know if you remember, but it's okay. It's not a major point. Yeah, add the gradients coming back. Yeah, for those who didn't follow, it's fine. It's not a big deal. Any other question? Okay, actually this is quite, you'll see afterwards that this is, in hindsight it seems, it's just an elaborate way of saying something very straightforward. Okay. Yeah, and as you saw in the animation, there's this layer depth, size of the output tensor, the layer depth is the number of filters. So if you have 10 filters, the output tensor will have 10, and one of the dimensions. Stride, which is the keyword used to say how much is the filter moving spatially. Okay. Maybe you want to make the filter move more because you don't want to do too much computation. You don't want to capture some very fine details in the input tensor. Okay. These are all choices. Zero padding again. You want to add some padding if you want to maintain some dimensionality. Okay. Suddenly you have an odd number of, maybe you have 7x7. You don't like a 7x7 input tensor. Then 7x7 cross some x input tensor. Then maybe you want to add pad. Things like that. But these choices you just make, using engineering. As in, these are hyperparameters. The filter parameters themselves you can figure out by backprop, and I'll talk about it soon. So here the stride is 1, padding is 0. Right? There is no padding, and stride is 1. It's exactly moving one step to the right. Okay. Okay. So that was the example. So let me just focus on parameter sharing. I've already kind of mentioned this before. That the idea is that if a filter is useful in one region, then it should also be useful in another region. So this is basically the key motivation for using a convolutional architecture. Okay, that so filters are essentially, you can kind of think of them as feature detectors. They are detecting edges or shapes or something. Okay. Detecting as in they just highlighting them more in the output compared to what's there in the input. Okay, that's what detection means, roughly. And because the same filter, so the idea is in an image, if a filter is useful in one region to detect maybe an edge, it's the same filter I can be used in other parts of the image to detect the same detect edges. Okay, so. And that's why we are parameter sharing. Filters are the ones which have the parameters, the weight parameters, and all the neurons on the same slice are sharing those parameters. Okay, while doing their local computation. Okay, which is add up, element-wise multiply, and do a nonlinear transformation. I guess I didn't show the slides, but it's basically the same idea. So this neuron and this neuron share if they are in the same this green slide, green matrix, then they are sharing the parameters. Okay, the 27. Doesn't have to be 27 here in this case, but whatever number of parameters. Okay. So the computation is very simple. So let's say all the filters were 3x3x3. Then if I have m filters as the output, m filters that I choose, then it's m times 27 plus 1. 1 for a bias. Typically, a neuron will have a bias parameter as well to just give an offset. Okay, and as you were pointing out, gradients need to be added up across neurons for a depth slice. So basically, think of the filter. I don't know if I've used we use this notation, but let's say basically W is arranged as a 3 cross 3 tensor, right? So you basically want the gradient of final loss with respect to this W, okay? And there are many other filters like this. And when you backprop, there are different computational nodes. There's a neuron N1, there's a neuron N2, but both of them are using the same W's, right? So W's are inputs here. Okay, the same W. Let me use capital W. This one and this one, right? Think of data as fixed, as in the data is in the x's. Let's say I have xi to just represent previous. I mean, to just represent the. Okay, let me not use little xi. To just represent the data part, right? So you're trying to move the parameters. You're trying to optimize the parameters. So everything else is supposed to be fixed. Data is fixed. Okay. So you're going to multiply this with this element wise. That's essentially what's happening in the convolution operation, and then pass on the result to future nodes and so on. Ultimately, you get to the loss value computation. So ultimately, you need to backpropagate, right? And when you backpropagate, the local gradient computed here and the local gradient computed here will need to be sent back to W to update. So that's where you add the gradients. Okay. Just go back to first lecture slide where I said if a parameter is related to two different nodes, then incoming gradients just add up. Okay. They will be of the same dimension. So filter has, I mean, we just chose arbitrary number. I mean, this is just an example saying if the filter has depth 3, width and height 3, then all filters have to have the same dimension. If I choose 10 filters, they all have to have the same dimension, because the output tensor has to be uniform. If one filter is 3 cross 3 cross 3 and then other filter is 5 cross 5 cross 3, 3 is fixed because input depth is 3, let's say, but they will give rise to different size matrices, so you can't really, put this nicely as a tensor. That's all. So plus 1 is just one additional parameter, which is a bias for the neuron, and so this is just multiplying the number of filters times 28.
When you're talking about gradients, we're talking about the gradients of the output tensor, right?
No, ultimately in all computations there's one loss value that you compute.
No, like when.
Yeah, gradient of the neuron's output with respect to its input.
Right, so gradient of the output tensor, right?
Of the neuron's output, yeah. I mean, you can think of every neuron output tensor, whatever its dimension is. Let's say it's 10 cross 5. Then these many neurons are there. Okay, so each neuron will have a local gradient. Okay, and so you can think of this set of gradients, which are these many in number. But you don't have to think of it in terms of tensor of gradients. Right. So think of each neuron is, so backprop is, the whole point of backprop is you don't have to think of a global view. Just locally what's happening. It's a node which is adding up, parameters with some fixed data, in this case x's, doing a nonlinear transformation. So you know what the local gradient is. Whatever its scalar output is, that scalar output, let's say, let me just draw that. So this is a neuron, scalar output z. Let's say input is x1, x2, okay, let me mark x2, x1, just to say that it's the same data point. Let's say x vector, and there is w1, w2, w3 that's getting multiplied, and there's a bias constant b. So you want to find the local gradient of z with respect to the first parameter, or if this is a vector, you can find the then you'll actually get a gradient, right? So if you stack them, so basically you want the partial derivative of z with respect to w1, partial derivative of c with respect to w2, and partial derivative of z with respect to w3, and similarly for b as well. Okay, so partial derivative of c with respect to b. These are the local gradients. Yeah, there's a lot of computation happening. This is true even for feed-forward networks, right? So, yeah. In feed-forward networks, the only issue is that the numbers are not being shared, so you don't have this. These W's, in convolutional networks, these 3 W's will also appear in another neuron, and in feed-forward networks, they don't appear. That's all. So the beauty of backprop is that you don't have to think of the global view. Every node, if you remember how to compute the local gradient, and as long as you backward pass the previous node's gradient, you just multiply and pass it back. Okay. Otherwise, keeping track of beyond 2 layers, keeping track of gradients is going to be tough. Okay. And okay, backprop is not just for neural networks. You can use it for any composition of functions. So for any set of computations happening in a sequential way, if it's differentiable, then you can think of backprop as a nice way to optimize parameters. Okay. Not necessarily neural networks. So if you're doing optimization, maybe you're doing supply chain planning or operations management or something else, like maybe revenue management. As long as the problem is continuous, as in variables happen to be continuous, in this case parameters happen to be continuous, you can use backprop actually. Although they don't use the word backprop there, they'll just use, let's compute the gradient and do a gradient update, right? Okay. Okay. Yeah, so this is just an example saying AlexNet was, so AlexNet was the first, I think back in 2012, that's the one which got some good performance, absolute performance improvement in image classification tasks. That actually had a filter size of 11 × 11, so it's a huge filter, okay? Not the ones that we saw. Input was 3 because it's RGB image, and they chose 96 number of filters in the first convolution layer. Okay. So these are actually just the filter weights, just like these are just the filter weights. So the weights themselves have been kind of are like photographs, right? Are like pictures because they have a 3-dimensional characteristic to it. So they just plotted it as images. Like some filters are trying to detect certain oriented edges, basically. Like if there is an input, there's a region in the input image which has the same pattern as this, then the output will be high. That's what detection means. Yeah.
So when you say about filter values in terms of, like, let's say one filter
Yeah.
So I mean the values of the filter or the filter answer, will it depend on the image as well as on the filter values? I mean the values of filter. If we want to detect edges in a
No, these were learned filters. So you had the ImageNet data, 1 million images, 1,000 categories. Used all the images, did backprop, and finally figured out some fixed candidate values for the filters. Now you're forgetting the data, and these are the learned filters. They happen to be this way. Okay. The filters themselves, there's nothing to do with the data. It is not part of this imagery, and actually it's a bit deceiving because I only plotted the first convolution layers filters because they just happen to be exactly 3 is the depth of the filter, so they can be thought of as images. But now the next input tensor is 96, so the next filter depth is 96, so I can't really plot it as a photograph. So this is just a way to kind of intuit whether what your neural network is doing, at least in the first layer, seems reasonable. Instead of handcrafting these types of detecting filters, at least it learned some type of filters like this. But some people say, if you do anything, you'll pretty much get these types of patterns. So it's not really unique to doing something meaningful. So anyway.
So what we're basically doing is taking a set of images and doing backpropagation on them and learning a few filters and then using those filters on different images to find
To classify.
Yeah.
Yeah, so all of supervised learning or parametric machine learning is all about having tons of data, compressing that into a bunch of parameters. Linear regression is just compressing it into a linear number of parameters. Nonlinear models like neural networks compress it into all these filter weights in convolutional networks, or you just think of it as weights in feed-forward neural networks. That's the whole problem. Okay, and then you reuse these weights or parameters for future classification, whatever. Right. Okay, so let's move forward. Let's look at the pooling layer. Pooling layer is actually very straightforward. The idea of pooling is to reduce the size of tensors, at least spatially, as you move forward. as we move forward in the neural network architecture. So let's say I said convolutional neural network is basically a sequential convolution layer, maybe pooling layer, maybe another convolution layer, maybe another convolution layer, maybe fully connected layer, and so on. So there were 3 types of layers, if you remember, that I had mentioned. You can stack them on top of each other as many as you can, except that the problem to optimize for the right filter weights becomes really messy. Okay. So, and the idea with pooling layer, so you can think of that as a layer which means that it has an input tensor and output tensor. Okay. And this layer's purpose is to just reduce the number of reduce the size of the output tensor spatially. Okay. And it's quite simple. So let's say the input tensor is 224 cross 224 cross 64. Okay. So the depth is 64. So the pooling layer will produce an output tensor whose depth is also 64, same depth, except that in this case it just reduces the output spatial size to half of what it was before. So instead of 224 cross 224, it's 112 cross 112. And how does it do that? It's again there are many choices, and one choice is as this. Okay. Let's say the input is actually not 224 cross 224. Let's say it's 4 cross 4. Okay, which means I need to half it into 2 cross 2, right? And the pooling is just as the name implies, you're basically somehow shrinking. Instead of these 4 numbers, you just need 1 number there. Right? So you can choose many different choices. In this case, it's called max pool, where it just takes the maximum of these 4 numbers and sets it over there. So think of this as a neuron, or it's not really a neuron, a computation node, which gets 4 numbers as inputs and just outputs the maximum of those 4 numbers. Okay, it's a computation node. Same thing with all these other things. There's this pooling operation also has a bunch of jargon. It's called a 2 cross 2 filter because it's pooling 2 cross 2 matrices of the input slice, and stride is 2 because it's non-overlapping. Stride is chosen to be 2, so how much you move, again, similar to convolution filter. So here, since you move 2, you're not really overlapping numbers. If you were moving 1, then you would take a max over these guys, it would be 7. Then you take a max over these guys, it would be 8. So it would be a 3 cross 3 matrix. Yeah. So if you want a half, maybe stride 2 cross 2 filter would be a good choice. Yeah.
So why are we doing this? I understand that.
Why are we doing this?
Yeah, and we're using the
Yeah.
this, the size of the tensor, but we are using information as well.
Yes. So I guess the high level idea is with models you will always lose information. So at the end of the day, you have data. You need to compress it into a model. It's not really thought of as compression, right? Linear regression. If you had a million rows of 3-dimensional data points, you just get 3 parameters at the end of the day, right? Linear regression with 4 parameters, let's say, with the offset. So that's compression. So you do lose information somehow. So yeah, here we are losing information. And why do we do this? Because if you keep the tensor sizes the same all the way to the end, then you will have too many parameters, basically. So this is all parameter reduction techniques. Number of parameters. So here there's really no parameter because it's a fixed function. It's just taking the max of 4 numbers. But with the output tensor, then if I add a convolution layer, the number of weights now kind of well, not the number of weights, but at some point you will have to interface with the final scoring, right? So at that point you will typically have a fully connected layer. If this tensor happens to be huge, then you will have lots of weights at that level. I'll actually show you what once I guess. So okay, two statements. One is pooling is trying to reduce the number of parameters, and you'll see the effect when I show the full layer, especially towards the last part when we use the fully connected layer. Yeah.
I understand this pooling stuff, but in the 74 it says operate independently for each depth slide. Why we need to do that? Why we not just pulling for the whole input neurons and then just apply that for every depth slide?
It's the same. I mean, operate independently. I'm just saying that it's. So this is not. So I don't know what you understood from this, but all I'm saying is you just repeat the operation for every slice. That's it. Yeah, it's the same pooling operation per slice. It's just that you're not compressing the depth. Now, it makes sense for images, but you could potentially also pool across filters if you want to. Maybe this is all choices for non-parametric functions to be more complex parametric functions. So yeah.
I understand if you go pooling in the forward direction, you reduce the
Yeah.
The objective is to do a backpropagation.
You'll backprop through the pooling operator. You backprop through the pooling node.
Generate the 4 numbers that you put in.
Backprop doesn't regenerate the.
I'm just trying to understand how will it just understand from it is now one parallel being 4, right?
Yeah. I will show you. So you're concerned about backprop, is it?
And
No.
my understanding is that something goes this way.
Yeah, going this way. So you got this. These were the input numbers. You got the output numbers. That's fine. Yeah. What is
How
the
does it even regenerate when it's backpropagated?
backprop? You just need to backprop gradients, not the numbers, right? So what is the backward? So this is the output. So let's say this is a Z. So basically there's A, B, C, D, and the node is basically taking max of A, B, C, and D, right? That's Z. Z is equal to this. So you're just asking what is the gradient of Z with respect to A, gradient of Z with respect to B, and so on, right? I mean the other two as well. So there's a 4x1 vector of gradient. Yeah. So you're asking how do we compute this for this function? No. I mean, so I think you are concerned about information loss. I mean, if I take a max, of course I forgot what these other 3 numbers are. So why is forgetting bad? No, I mean, so any neural network or any function, any classifier, it has to forget, right? I mean, if the input image is 1000 cross 1000, ultimately I have to compress that into saying whether it's likely a cat or a dog. That's just going to be 2 numbers. Probability that it's a cat, probability that it's a dog, or so 2 scores. So I'm losing a lot of numbers in between. Right?
So anyway, we can do anything across all the different parameters. Like we can take average of all numbers or maybe the minimum. If we have to be
Pooling, yeah, you can choose average, you can take min, you can take
so
max.
it has to be similar across all the input parameters.
These are just time tested and popular and working choices. You can try other things and see how your network works.
Is this an alternative to the convolution layer?
No, it's not an alternative. It's a layer which succeeds a convolution layer typically. Yeah, I mean, it's not an alternative. All these layers are basically, think of them as taking an input tensor, doing something, giving out an output tensor. In this case, whatever the input tensor is, it's going to maintain the same depth, but it's going to reduce the spatial dimension by a factor of 2, for example. That's all. Tensor to tensor. Convolution layer is also tensor to tensor, right? Input is a tensor, output is a tensor. But there are weights associated, there are parameters there. Here, there are no really parameters because the function is, and the function doesn't have any parameters, right?
I guess the question is, I don't
Yeah.
understand what function the pooling layer.
It's just coarsening things, right? It's just coarsening numbers. It's trying to reduce the number of, like in the, if you don't apply the pooling layer, the next, there is no reduction in the tensor. So the next, the next convolution layer, for example, will have to work with more data, more inputs. That's all. All of these are hidden layers, yes. Why do convolution again and again is a question. Do I have a picture for that? Okay, actually I think at this point I want to kind of use this. Let's say 3. So this is an image. I mean, I think actually Swapnil shared this, right? You shared this, and nobody clicked on this. Okay, this was on Slack channel a few days ago. So here actually you can see, I'm not even sure whether it's it is actually so it is actually a convolutional neural network, at least the first few layers. So here you can see, right? So what are we seeing here? So this is the input image. Okay. This is the activations. These are the computations done by the neurons. So we are not looking at weights at all. Okay. We are not looking at explicit the weight matrices. We are just saying for this input, what does one layer of my output tensor look like? I don't know how many, maybe 5, 6 output, 6 filters. Okay, so each filter is given here 1, 2, 3, 4, 5, 6. And these are the filters outputs. Filters outputs are just matrices, right? Whatever will be the depth of the filter, filters outputs are just matrices, and here these are the 6 filter outputs. Now here it looks like there is this pooling happening. So from this big matrix there is a smaller matrix. It's just averaging. I actually haven't seen what's happening in the back of, he has a paper, the person. Okay, he has a paper, so we can look at it. But so there is a pooling operation happening, and then again another convolution layer, happening. Okay, here in this case, I don't know, 4, maybe 20 filters. Why? Because you can always do that, right? I mean, in fact, I guess there is an engineering answer to this. People wanted to make really, a lot of compositions of functions, because all these other parametric models like SVMs or even kernel SVMs, they are all shallow networks, in the sense there is no multiple function composition happening. Here you're doing some nonlinear transformation. Again, you want to do some nonlinear transformation, so as to have richer parametric class of functions to predict an output. Okay. So this is why I guess people may ask, what is the deep part of deep learning? So this is the deep part of deep learning. You can compose functions. Compose functions in the sense you can have a convolution layer on top of another, another convolution layer, have another convolution layer. You can probably have hundreds of convolution layers, and then have a fully connected layer and a scoring function. Except that if you have too many layers, the challenge is you cannot really tweak these weights. You cannot do really backdrop and get these filter weights to be such that you can do really good prediction. And that was what was the bottleneck for since the CNNs were invented in 80s, so 80s to 2000s. That was the issue, that there were no compute resources available. Now with the GPUs, okay, it's not working. Now with GPUs you can actually stack functions. That's the deep part of deep learning.
So, for all of that, we're trying to get a better parametric function that helps us estimate the classifier.
Yeah, I mean, so when you think of neural networks versus linear classifiers, or logic regression, or LDA, or random forest, they're all parametric in some way, and you want to change these, and each parametric class represents certain functions. And if you are just trying to, when you pick the right parameters, you're just picking one function from this parametric class of functions to make a prediction. That's the, very high level view of what we are doing with supervised learning. We're just picking functions, right? Happens to be whether it's a linear function or a non-linear function, which is a neural network, is your choice. Depends on a lot of things that you learned in maybe 575. Here it happens to work really well for images. So I don't really have a very good answer for why having a second convolution layer helps, actually, because in theory you are supposed to approximate any function with just one layer. In neural networks theory, people have proved in the early 90s or maybe 80s that one layer neural network is a universal function approximator. So any function can be approximated by one layer neural network, but it doesn't happen so in practice. So this is the engineering or empirical way of finding good classifiers. Okay, so here actually, I think okay. So you can see like pooling happened here. So some arrows are drawn. I don't know. So here convolution is happening because this some filter is applying on all input depth to compute one number there. And if you I don't know. I don't think this. In this case, I don't know what's the issue. Some inputs are 0 maybe. And then there is actually a fully connected layer here. Okay. So if you see, since it's a fully connected layer or just a regular feed-forward neural network layer, it's just a bunch of neurons, and every neuron is connected to every input. Okay, that's why you see a lot of these lines. And if you did not do this pooling operation, maybe you would have huge these sizes and maybe double or quadruple the number of parameters, which are these parameters are unique per neuron. So if you had 100,000 of these, then you're really, and if it's 1,000 layer, then you're really looking at a million numbers here. So that is a bottleneck, and that's one of the reasons why we actually introduced convolutional layers to reduce the number of parameters. Okay. If we had used the fully connected layer, then number of parameters would be too many.
Over here,
Yeah.
we have 2-3 questions. First, we did the first convolution layer,
Yeah.
and that has I think 6 filters over there,
Yeah.
right? And then on those 6 filters, we have a pooling layer. Now that
Yeah.
pooling function, is it the same for each filter or is it different for each filter?
That's also. I mean, I think typically they use the same pooling operation. So here I think it's just maybe max pooling or average pooling. Yeah, they are using the same pooling function.
Okay, and this pooling
Typically,
function,
but it's not necessary that you use the same pooling function, but you can change it.
okay, and that's an engineering choice, or is that done
All
by-
practical like Keras, TensorFlow, and all these things. They have they make you only choose one pooling function, like a max of 4 numbers, let's say, for all of these.
So that's an engineering choice.
Yeah.
Okay, and so now the first
There are
one-
hundreds of engineering choices here. That's not the only choice.
Yeah, and as in this, that's not done through backpropagation, right? Like how we.
No, but you have to backpropagate through that node. So that max function doesn't have parameters, but you have to take that max function's output with respect to its input arguments. And max function, if you remember max of 0, z, we already took the gradient of that. The gradient was, if z was negative, it was always 0, and if z was positive, the local gradient was 1. Now it's just a change. It's now a max of 4 numbers. Yeah.
Okay, so after that,
Yeah.
after the first pooling layer, we have the second convolution layer.
Yeah.
That second convolution layer has filters only on one of the pooling, like how I have 6 pooling outputs now. So my one convolution, the next convolution.
Yeah.
layer, one
This is a
filter-
convolution layer. It may have
Right.
20 filters here. It has 20 filters here. I think.
Right, so one filter is not limited to just one pooling output. It can have the input as
Yeah. So filter depth. Remember, input depth is what 6 here. So each filter's depth is also 6. So it has to look at all the. I mean, here I don't know if it's an issue with animation or if the numbers are 0, but it has to look at all the filter. All the input depth. All. Like if it's looking at one region, let's say this region, it has to look at that region for all the input tensor slices. Right? Just like in the previous layer, it was looking at. Yeah, in this case, there was only one input layer, so that's why we didn't have that. Yeah. Any other question? Any questions? I think we're going very slow. What's the time? 7. Okay, let's take a 10-minute break. Okay, and the last layer from last time was a fully connected layer, which we already know, so we are not gonna really discuss it too much. So there was another animation, but we've already seen one animation, so let's this thing you can see it offline. Okay. So CIFAR 10 is a data set I think we saw in the last lecture, and you'll also try to use it in your assignment. And it's out. Assignment is out, so have a look at it. Yeah, so that concludes this lecture. I mean, in the sense, the previous lecture. Let me just save, I guess, somewhere. I'm not sure which directory to save, but anyway. Okay, so today we're gonna kind of really not, anything technical. It's gonna be mostly intuitive, or maybe not. We'll see. visualization. So we'll try to kind of understand CNN. So the thing is, in the usual classification, setup, we had features, interpretable features, potentially, the raw features were at least interpretable, and we kind of could guess what was happening. At least for linear models, we could guess, what was happening with each feature. Here, input is really an image. We haven't really converted it into features at all, and we just threw it into a whole, black box as a CNN, and hopefully we got some scores. Through which we got computed a loss function, at least some training data, back propagated, updated the weights of this, huge black box, which is a CNN, and hopefully the weights got to some nice setting such that this thing, can do good classification. Essentially, that's what we did. So next we'll try to, so in the next, an hour or so, we'll try to visualize or a little bit debug any of the CNN. Let's say you already trained the CNN. Now the weights are fixed. Now you want to understand how is it performing. Okay, the weights are fixed. It's a learned model, and then we'll look at something called transfer learning, where you don't train a CNN from scratch. It's basically saying that you already know a bunch of, maybe somebody else trained the CNN for hundreds of hours or thousands of hours. You just use their weights and maybe only change a few of the weights. So you only do gradient descent on a small set of weights. Okay, and third part we'll see if we get there. So it's not really a review. So this is just just a recap saying, last time I kind of motivated by saying, let's say there's an input layer, a convolution layer, a pooling layer, and then I directly said let's connect it to a fully connected layer. So I only said this and then like this. That was the running example from the last lecture slide. Here I've added another convolution pooling layer, another convolution pooling layer, and two fully connected layers, one after the other. Okay. So if input was directly connected to this, then this would be your 3-layer feed-forward neural network, as in 2 hidden layers. Okay. Yeah. And I mean, this is still a diagram. It's not probably a real CNN. So here again, there are 2 convolution layers, then a pooling happening. 2 convolution layers pooling, 2 convolution layers pooling, and number of filters is 10. So that's why you have 10 outputs. It's 10 matrices. And in this case, you're not looking at weights again. You're looking at an image's filter output. Filter times image. You have a single number. That numbers are going to show. They look like basically they're detecting some features of the car. Maybe. And ultimately, you need let's say it's a 5-dimensional 5-category classification problem. Then you want to have scores. Maybe the score for car is high. Okay. That's how you want to set the filter weights. And in terms of just a recap on parameter counts, so let's say the input tensor is 90 times 90 times 10. So this is not really the input image, right? This is some intermediate tensor which has 10 as the depth, and say we have 5 filters. So once we choose 5 filters, the output depth is 5. That's fixed, and this has to be the same as the input depth. So 10 is fixed. So let's assume we choose the filter size to be 3 cross 3, and stride is 1 and zero padding is 1. I don't know if you remember, if stride is 1 and zero padding is 1, then the output sizes happen to be the same. So it's going to be 90 cross 90. Okay. So the output size is 90 cross 90, and since we chose 5, the output depth is going to be 5. Okay. That's the output tensor. In the sense, essentially, we have these many neurons, except each neuron doesn't have independent weights. They have number of weights, which is this times 5. Okay. In fact, I guess that's what I wrote here. Plus 1 bias term for each neuron. I mean, for each filter, there's one bias value. So these are these many number of weights, and if you compare it with let's say a fully connected layer, then you have something like this. Okay, too many. Okay, so backprop. I think I mentioned it previously as well. If you backprop through a pool layer, it's basically backprop through this max operation if it's a max pooling thing, then if it's a 2 cross 2 max pooling, then something like this. This is the function you need to backprop. And convolution layer, again, it's matrix multiplications are happening. Convolution layer is really nothing different from a regular feed-forward neural network, except the weights are being shared. So whatever backprop thing that we saw for feed-forward networks, it's the same here. Okay. So it generally will not do this by hand, but sometimes there is possibility of going wrong and so on. So should be careful. Okay, so let's directly get to visualizing CNN. So basically, the common criticism is, what are we even doing? It's a huge non-linear complex function composition of a bunch of functions, essentially. I'm thinking of like each layer as a function because it's transforming something to something, right? So mapping something to something. And so, not really 4 attempts, maybe 5 attempts. So we'll try to kind of understand what's happening. Once a CNN is already trained, okay, so we did backprop, we got some best parameters for each filter or all the neuron weights. Then we can do a few things, and that's what we'll try to do and one of the things that we've already seen is look at activations. So I'm going to tell what an activation is. Activation is nothing but this thing, sum over Wj xj plus bias. So if a neuron had a bunch of weights related to it and a bias term related to it, and this is called the activation. This or the transform version. I'm not really sure. Is the transform version? Okay. So I guess some of you are already experts on neural networks, so it's going to be some transformation. Okay. Yeah, and this I guess is called pre-activation maybe. We can also look at weights, but as I think I was pointing out, for input image, because the input image depth is 3, the first filters happen to be of depth 3, so you can at least look at weights. But otherwise, it's kind of hard to kind of just look at weights as a matrices. Even if you plot the matrix or just look at the matrix, just look at the tensor, it's kind of hard to understand what's happening. And then we look at a couple of other things. So let me directly get to the next, first type. And this is where I wanted to show the animation. I've already shown it. There's another tool that I guess some researchers came up with called deep visualization tool. So they are trying to show activations. They pick up some layer. I guess here some CONV or something, and this is the input. Okay, real-time video, and I don't really know which one is the. So these are all activations of some layer. So the tool does a lot more. So I just put it here because you can kind of look at it later on. But so what exactly is activation? So the simplest thing, again, just in terms of intuition, is that if you've already trained the CNN, weights are all fixed. Let's ignore that. And here we're just trying to look at what happens. Like if I pass the image of a cat, what's happening in terms of outputs of the filters at each layer. So I guess this is the first convolution layer. Maybe it has 6 times 6 filters. Okay, 36 filters. So you're just looking at the outputs of each filter slice. Okay, hoping that the goal probably is that each filter hopefully captures some aspect of the cat, which ultimately is passed on to the next layer and so on. So here there are very too many filters. You're just looking at the outputs of each filter. I don't know. So this is just useful to kind of, let's say you do this for many different categories that you have, maybe 10 categories, and you see that certain parts of the outputs are never, there's never a white pixel, which means that all those neurons are probably not even outputting any one or anything positive, right? Let's say it's a ReLU nonlinearity, then it's not outputting anything positive. It's always 0. And those are called dead ReLUs. So that means you've kind of initialized your initial set of weights so bad that they're not moving out of that bad weight, bad parameter region. Okay, some these are just ad hoc ways to figure that out. There's nothing much to say more about this. What is the disadvantage of using a lot of convolutions?
Is there a
No, the disadvantage is generic to any very highly rich parametric family of functions, right? It may overfit your data, completely memorize your data, for example. Things like that. So disadvantage is overfitting with all these models. Yeah. Disadvantage, there's computational disadvantage as well, in addition to model richness, which leads to overfitting, is that you can't really do gradient updates because the loss surface is going to be, so moving from one weight one bunch of weight numbers to another bunch of weight numbers, you need gradients, and you can't really do gradient descent once you have too many convolution layers. The gradient descent doesn't work. Okay. And that's why most people spend a lot of time to figure out, fine tune, figure out how to make the gradient descent work and get to good parameters.
So when you use a lot of combination layers in the end, is it generalizing my data more, or is it specifying my data more? Like, is it increasing the specifications, or is it increasing the generalization?
I have not introduced generalization in this class, but I mean, those of you who has not done 575 last semester. Everybody has done 575 except for one, just one. Oh, people have not done 575. So basically, this is this. I think so. When she was asking about generalization versus being what is it, specific?
No, I'm just using a normal term.
Okay, you're not using the generalization.
No. I'm
Okay.
using a normal
Okay.
basic English word term.
So what is meant by generalization then?
In the sense, if
Yeah, if your models just memorize inputs, then it's I guess it's not generalizing. If the models if the model, in this case a CNN network, is only keeping those features which happen to be general across that object category or something, then it's a good one. Hope is that all models are supposed to do that, generalize, and there's a formal notion of generalization that hopefully even these neural networks also have. Okay. You're asking if having more convolutional networks helps in generalization or being very specific. They should help. So as I said, more convolutional layers just make the function, the composition functions as too many, so it is a richer function class. Okay, if you think of functions, in the sense that many parameters, so you have many more degrees of freedom to tweak so as to make your classifier better. That's what I mean by richer function class. You have too many parameters, so you have more convolution layers, then you have more parameters. But it's not clear whether it will generalize or be specific or whatever. Yeah.
Coming back to visualizing the activations, how does it work? You said we actually look.
Yeah, this is a very painstaking process, right? They just pick one image and try to pass it through their learned CNN and try to figure out which neurons are turning on, basically. Yeah. Yeah, how else can you?
So, like you said, if I have 10.
No, you can do this for even shallow networks, right? You can pass a particular thing and see what's getting detected or not.
Like, how do I figure out how many inputs is a good, this is not important?
No, you just take a canonical input for a category. Let's say they're cats versus dogs. You take a cat image and see what things are getting fired up in different layers. Yeah, these are all diagnostics, trying to understand what's happening inside, right? I mean, at the end of CNN training, you have a bunch of weights. You can just look at those numbers. You probably won't understand much, or you can try to kind of debug, what's happening in CNNs. Here is visualization of weights, which really is as I said, I had pointed out before, for first layer convolutions, you can actually visualize and at least they are images because the input depth is 3. But second layer is just visualizing matrices, so it's really not useful. So in a sense, that brings back to the point. You train the model, you have a bunch of weights, you can visualize it this way, but it probably is not very helpful. Okay. I mean, if your trained model doesn't even have this type of thing in the first convolution layer, maybe you're kind of off quite a bit. Okay. Maybe that's one takeaway. The third one is actually visualize something else, which are activations. Okay. Now it's a more interesting way of doing things. Now you'll use all your data and try to visualize what's happening. Given the learned CNN, what's happening? Is it doing something reasonable? And so for that, I need to introduce, I guess. We just defined activation in the previous slide. Activation is just the output of a neuron. So let's take the activations of the last fully connected layer. Okay. So if you remember, there was this conv leading to pool. Maybe I just connected to a fully connected layer, and then I got scores. Okay, maybe it's 10 dimensional for CIFAR 10. Okay, so let's not go to the computation of this 10-dimensional vector, but just before that. So this would be that operation. So let's say score is 10 dimensional, 10 cross 1. Then W would be 10 cross whatever is this inside. Let's say it's 1024 or something. Let's say 1024 neurons. Then this max of 0, h would be that activation vector. Okay, you can have one activation vector for every training example that you have. Right? For every xi, basically I have a AI is what I'm saying. Okay, right? Are people confused at this point? No. So it's just a vector, which is this vector max of 0, h. Okay, and then what we're going to do is actually do something like a PCA. We're going to project, and this let's say AI is 1024 dimensional. We're going to project it back into 2 dimensions to actually visualize. We can only visualize things in 2 or 3 dimensions, right? So we'll do a projection. Typically, I guess it's called embedding. Is also a name for this. Embedding vectors in high dimensions to low dimensions, in 2 dimensions in this case. And of course, you just want to don't want to just drop. Let's say you have a 1000-dimensional vector. You can drop the 998 coordinates and just take the first 2 coordinates. That would be one projection. That may be a bad projection. So you want to have some properties preserved, and in this case, we want to have distance properties preserved, because the idea is to see if we can. Let's say there are images of cats, images of dogs. Hopefully, when they're projected down, they're 2-dimensional vectors. Hopefully, the cat vectors are close to each other and dog vectors are close to each other, rather than cat and dog vectors being close to each other. Okay, in 2-dimensional space, that you can visualize. This is all diagnostics. Okay. So here is the image of images. I will collage. So AlexNet was, as I said, is a really 5-year-old neural net, convolution net, and the output of the layer before is the last layer or last one is 4096 dimension. Okay, right? The fully connected layer had 4096 neurons basically. So the activation vectors are 4096, not 1024 in the previous example. Now those 4096 dimensional vectors have been projected down into 2 dimensions. Okay, on a 2D plane, which means so that's not being shown here. So these guys were projected into 2D plane. So let's say the plane is whatever unit box. So all these points were put in here. There's another point which goes here. All these points were put here, right, in 2D plane. Now what we do is instead of those points, I'll tell you how those are put, but instead of those points, I'm going to replace the point with that image and just beautify the 2D plane a little bit. So let's say this here, it looks like an image, but this image is for an equivalent, for a point that fell here for this image because of its activation being projected down to them. So basically, all these images are located at those coordinates where their 2-dimensional projections, 2-dimensional embeddings went to. Okay, and so AlexNet was for, I think, ImageNet, and ImageNet has 1000 categories. So, and you can see, at least diagnostically, that certain types of categories are close to each other and certain types are not, and so on. Okay. This is just a diagnostic to kind of see whether the embeddings, the activation vectors are capturing this information about each category. Okay. So, for example, maybe this is something else. I don't know. You can visualize. This is not really high resolution. There is probably an high resolution one in this link. You can check it. Okay. And the distance preserving property, like basically they're trying to say in high dimensions, in 4096 dimensions, maybe a cat vector and another cat vector are close to each other. Then in the 2-dimensional plane, they should also be close to each other. Then only you can visualize it. Some property has to be preserved so that by looking at this image, you can say, okay, this CNN probably learned something interesting. Right? Probably is a good classifier. Right? And that projection operation happens to be a nonlinear projection operation called TSNE. Okay. How many of you have seen TSNE before? How many of you have seen PCA before? How many of you have not seen PCA? Oh, you did it at 575? You haven't taken 575. Okay. Are you taking 572 right now? You're directly taking 576?
Yes.
Okay. So so you could also do PCA here instead of TSNE, but TSNE happens to have some nice buttons. Okay? And people use it. There are many nonlinear projection techniques. So these are called embedding techniques. Okay. This is not critical to our discourse. So if needed, I'll add some notes about it in the course website. This is another interesting diagnostic tool, visualization by understanding how CNN behaves by occlusion. So what we do is, again, CNN is learned, weights are fixed. Now what we want to do is we want to find which part of the image is actually leading to a certain classification, maybe a correct classification or a wrong classification. Okay, and then so how do we do that? So we actually look at so we have an image. We're gonna try to occlude it. Occlude it means change the pixel values to maybe all zeros or all ones, and then see what is the score or the transformation of the score, which is the probability value. You remember, score was transformed to some more SJ, something like this. So let's say this. So what the correct class is. Let's say the correct class or category happens to be I. I for this particular image. Maybe it's a cat. Then you just look at this probability. As you move the occlusion, you want to see whether this probability is changing or not. And maybe if you cover the cat, this probability should ideally not be, it should not score cat high. But if you keep the cat, then hopefully the score is high, something like that. Okay? So let's look at some examples. So in this case, so this is a Pomeranian picture. Maybe it's from ImageNet, I'm not sure. And in this case, Carville, in this case, Afghan Hound. So this is a dog here. And so here there's moving a small box, this gray box. Okay. And they're saying if I keep this box here, okay, and pass this through my CNN, what is the probability that it's going to be classified as a Pomeranian? Okay. If I move this box onto the face, the probability that it's going to be classified as a Pomeranian is decreasing. Blue means low probability, red means high probability. Okay, higher score as a Pomeranian, lower score as a Pomeranian. So you're occluding the actual features needed to kind of classify it as a Pomeranian. Okay. This is a nice diagnostic tool. For example, like here, if you're really occluding the car wheel, only then it's kind of saying it's not a wheel. Okay. But it's also picking up other features. If you occlude this part, maybe this, forget about the label here, but if you occlude this part, it's actually losing the confidence that it's a wheel. So it's picking up other features, nearby features, which kind of influence its classification, scoring of this image. In this case, if you occlude the dog itself, of course the probability is going down. If you occlude the lady, the probability is also going down. Okay, so that's clear, right? That's kind of it's a diagnostic tool. And the last one is synthesizing images themselves. Okay, so here again, this is a laborious process. You first pick a neuron of interest. It's very difficult to pick a neuron of interest. There's so many neurons in the network, but maybe you pick the one at the last, almost where you had activations, right? 4096 or 4096. Pick one of them, and then you kind of find images that activate that neuron the most. So you want to find what would be the input. So now it's a different optimization. Now you're asking what should be the input image that ensures that neuron's output is 1. Let's say it's a sigmoid nonlinearity, so output can only be at most 1. Then you're asking to make it 1, what should be the input image? And so the way you do it is again backdrop. Now you're actually filter weights, the CNN weights are fixed. You're actually just changing images. So your images are now a parameter. You're moving from image to image, and you're trying to figure out and doing backpropagation. Like you start with an image, you get a value of 0.5. Maybe it's not the highest score. Then you take the gradient of 0.5 with respect to this image. Get the gradients, put up the image to another image. Look at the score. Maybe it's 0.6. Again, backdrop. Get a different image, and so on. Right. Apparently you're supposed to see it with some image priors and not just start with random noise. Otherwise you don't work. It doesn't work. Apparently this technique. And here, huh? Like how? So which image? Like what do you start as initialization? So at which image do you start doing this backdrop operation? because images are not noise, right? Not every pixel is randomly chosen to be between 0 to 255. That's not going to be a naturally real world occurring image. So it's a hypothesis, I guess, that the naturally occurring images they belong to some unknown low dimensional, it's called a manifold. But anyway, so there's some structure in this real world images, right? They're not like every pixel is randomly flipped from 0 to 255. You pick a value and that's going to be an image. That's not going to be a real world image, right? So that's all it means. This is just a biasing of your search starting point. These are actually, it's supposed to capture something. It's not even clear here what's happening, but I think the next one has something interesting. So here you're actually trying to so you picked a neuron and goose. So this is the image which maximizes the activation for that neuron. It happens to be like balance of some bird in this case, and a different neuron has a different pattern of image that actually activates it the most. Okay, it's a way to kind of understand. Okay, different neurons are kind of specialized, especially if you're multi-category optimization, multi-category classification. Then you're basically saying different neurons are picking up on different aspects of input images. Okay, because if their scores are high, like this is like the activation vectors, right? If the scores are high, which eventually will convert to transform to a probability that the input image is actually a goose or something, right? So that neuron is probably responsible for birds or for maybe just goose or something like that. That's just the interpretation. No, the neuron's output. Neuron's output is a number, right? One scalar value. You want to make it as high as possible. Yeah, I said pick the last layer, let's say last but one layer, 4096 neurons. Remember the activation vector? Pick one of them and do this. Yeah, it's a laborious process. Yeah, actually you don't even have to go all the way to the last layer, so you can actually do that backdrop up to layer to figure out what's being picked up. Maybe there are some higher order features being picked up, like I don't know what it is. Some higher order features being picked up. But the thing is, you can't really visualize them. There's some engineering here to visualize them because these are really these are tensors, so you're just looking at slices. Supposed to look at slices, but then I don't know how to make colors. So
how is it different from visualizing?
We visualize all the way to the end. Instead of that, you can visualize in between, right? What's the pattern in the input tensor that's giving the maximum, maximizing the output of a particular neuron. You don't have to look at all the way to the input. You can ask one, anywhere in between.
Okay. How is it different from visualizing just activation?
Visualizing activations for images in our data set. This is not images in our data set, right? We are just asking for imaginary images which are maximizing certain neurons outputs. Okay, and I guess some variation of that is basically look for images in my data set which activate a neuron the most. Like pick a neuron and then say, tell me in my data set which image is the one which is activating this neuron the most. Yeah, there are different neurons, I think, and for each neuron, I think they're just seeing which image in the data set is activating the most. Okay. So I don't really know how to do this well, but I mean, basically, you can see that there are some neurons which activate for houses the most, and there are some neurons which activate for faces of dogs, things like that.
So the numbers on these are the output of the neuron, the score?
Yeah, I think so. Yeah, I have to look at the reference. Yeah, it's basically these are ways to diagnose. I mean, images, the thing is, they're not interpretable features. I mean, at least except for the initial layer, right? So it's if you have a large image data set, then these are some ways to kind of understand what's happening. I mean, if you're doing the regular way, which is to create handcraft features, like I think I mentioned something like histogram of oriented gradients, histogram of colors, and things like that, then you're just doing, let's say, an SVM, then you're just getting a bunch of weights, right? So there is really not much interpretation stuff to be done there. I mean, they may still not be interpretable, but at least it's kind of, there are very few parameters in that such a model, unless you're looking at kernelized SVM. These techniques? Yeah, I mean,
which ones? Are there any threshold ones?
no, these all are basically from the past 5 years of work, right? I mean, the first CNN which actually did well, therefore we are looking at this, is pretty new. So if you're asking about production level practices, maybe not. Production level, in fact, other than the top, few companies, I don't think many people bother with these type of things. They use pre-trained models and so on, and we actually look at one of them today. They may not have resources or need to do this type of debugging. Okay. And for many companies, they won't train CNNs from scratch, and they'll use pre-trained ones, and that's the concept of transfer learning. Okay, transfer learning applied to CNNs. Okay. Okay. So transfer learning is actually a very nice idea. Actually, I guess it has more bang per buck compared to many techniques out there. So it's basically like trying to dispel this myth. Like, you need to have a lot of data to use or even build deep neural networks. That's not true if you have access to pre-trained models. And if you have access to pre-trained models, you can do a couple of things. One is to do something called feature extraction, and the other thing is to slightly modify the pre-trained model. Like, somebody has trained the CNN for you, some CNN for you, and you think that CNN was trained on really nice images, and your problem happens to be a subset or something related to those images, then you can actually reuse the learned model, as in the weights of that CNN. Okay, and this is loosely termed as transfer learning. And transfer learning in the non-CNN context also means a lot of things. In other supervised learning tasks, in reinforcement learning tasks, and so on. But we are just talking about transfer learning for CNNs. Okay. Okay, so what is feature extraction? And feature extraction we have already seen. It is as follows. So you get a pre-trained CNN. So the question is, where do you get it from? A lot of these, at least historically, people release their pre-trained models unless it's making them a lot of money. and so AlexNet, for example. AlexNet was the one, I think, which did really well on ImageNet in 2012, and VGG, I think, came second in 2014. And there are subsequent versions called ResNet and InceptionNet maybe, by some of these top tech companies. So they release the model weights basically. So you know the architecture and the weights, so you can just set them up, and you can always do classification. But here what we are going to do is we'll get the pre-trained CNN. We'll remove the last fully connected layer. What does the last fully connected layer do? Whatever is the its output has to be the number of categories that you want to classify for. Okay, so you're just deleting that, and then the previous value is what I defined as activations, right? So a different word for activations, I guess, a more general word for those activations is called embeddings. So I went from an image to a 4096 dimensional vector. That vector is called an embedding. Okay. Activation vector actually. So basically we deleted this last fully connected layer, and here we're getting an activation vector, right? And that's let's say 4096 cross 1. Okay, I mean, we're not going to collect these activation vectors. We are just going to okay. No, sorry, I apologize. So you have new training data. Then for each training data point in your training data, you will get these activation vectors. Okay. So basically, you are transforming images to these vectors. Okay, and then we'll just use anything else. You can use a shallow model technique like an SVM or a linear classifier or LDA or something like that to do classification. Okay. So yeah, the interpretation is that basically you're thinking of this activation as an embedding of the image in some high dimensional space, and once you have the equivalent embedding of the image in a high dimensional space, you can do LDA or logistic regression or something like that here. Okay. Yeah, it's the representation of the image. It's also called the CNN code. Maybe this is less popular. I've never heard of it. Activation vector. Okay. How is it performance wise? I think I mean it has been used successfully. If you're asking empirical success, yeah, it's been quite a successful technique. Yeah. I mean, it doesn't make sense to train a network. So AlexNet, has quite complicated architecture. You can imagine how many weights are there at every layer, right? You may not want to train this from scratch because it's a highly if you don't start with a good set of weights, you may get to a wrong. You may not get good performance accuracy and so on. So somebody else has done the work for you, and since they have worked with imaginary data set, if has 1,000 categories, if your specialized problem also has roughly the same type of categories or a subset of those categories, you can just reuse the pre-trained model.
So when you use the pre-trained model, don't you change weights of the existing model, or don't you just change the final activation?
No, basically we are just using it as a transforming function, right? It's a fixed pre-trained model, so the function is fixed. For every image, I'm getting a vector, and I'm throwing away this pre-trained model, and I'm just working with these vectors in a regular supervised learning task. Like I can just use LDA on these 4096 dimensional vectors. So I have a 4096 dimensional feature vector and a label. So this is my new training data, and I can just do something simple. KNN. Maybe KNN is not a bad idea, but LD logic regression, let's say. You don't need an API, right? You get the weights, so you know exactly. Oh, how to import the weights and create the You can do all this in Python. Maybe next time I'll demo VGG16. VGG16 is available online. The weights are about 500 MB in file size. It doesn't have too many parameters. Actually, there's a graphics maybe on this lecture notes or next lecture note which tells you how many parameters are there in these contest winning CNNs. But we can actually do this in Python. This is the easy part. I mean, this is just like downloading a model and just running your images and getting vectors, right? No, I mean you can use. I mean they are essentially feature extractors, basically, right? And I guess that first one was just first one is feature extraction, right? Yeah. This is what I just said. Input the activation vectors to any linear or non-linear classifier, right? I mean the idea is I guess a rule of thumb is that generally the activation values at the lower layers are going to be very generic, and higher layers are going to be specific to the data set that it was trained on. Like AlexNet was trained on ImageNet data set, so those 1,000 categories. So the activation values here would be kind of trying to detect features of those 1,000 categories. So if your problem happens to be very different from that, you can still use the pre-trained model, except you may want to use something like output at this point or something like that. Lower level features, image features. You can still use it.
How do you understand the logic? Like where to break up
It's your choice. They're only like, if it's let's say 10 layer network, you have 10 choices, you can do cross validation, figure out. Right? Okay, the second type of technique, which really doesn't want to explicitly take care of explicitly kind of look at activation vectors, is really to retrain, but you don't retrain the whole CNN. Okay, you don't update the do the gradient updating for all the weights in the CNN. Okay, you only fine tune either additional layers, so you tack on more layers on top of the CNN. So you break. So the last layer of the pre-existing CNN, let's say AlexNet, was 1000 dimensional, 1000 categories. You can chop off that. Okay, there is going to be a previous fully connected layer which is 4096 dimensional. Now you can always connect your fully connected layer, which will be, let's say you have 10 categories, then you can connect a 10 10 neurons basically there, and just train the weights for that connection. Okay, there will be a weight matrix connecting the 4096 to 10 dimensional scores. So those weights you can train. Okay, that's called fine tuning. I mean, it's just saying don't train the whole thing, just train part of it. Okay, like in this case, maybe you just retrain the weights of these two blocks, these two layers. Okay.
So do we only add a fully connected layer, or can we add some convolution?
At this point, I guess I kind of did not stress why convolutional pooling makes sense for images is because of the spatial invariance aspect. So in an image, you want to try to detect a cat, whether the cat is at the top left, top right, or in the center, it doesn't matter. So somehow these filters are basically, because they are small, looking at small spatial regions repeatedly, you're gaining good performance at the expense of very small number of parameters. Okay. At the last fully connected, an activation vector which is 4096 dimensional, there is no notion of spatial. There may be spatial invariance aspect in that vector, or maybe not. So it's not clear whether a convolution layer with a pool is a good idea there or not. You can use it, or maybe not. You can use it because the number of parameters is less, but it's not clear whether it's going to be useful. So that's why you've not really seen convolutional neural networks being the best in every category, right? If you had regular data, tabular data, let's say, they're not thinking of using convolutional neural networks. I mean, some people have tried it. There are some papers like that, but it doesn't make much sense. I mean, unless there is some intuition that there is some structure in the data for which convolutional layer makes sense, it doesn't. You can just use a fully connected neural net and be done with it. Yeah. CNNs can be used for temporal data as well, but it's just a question of but what you're trying to say is I can afford a loss, and therefore I can use CNNs. That's not I can go to lower resolutions and CNNs are a way to do so. That's not the reason. So if you're asking whether we can use CNNs for temporal data like sound or sound and videos, let's say, you can use them, because videos still are like slices of images. Sound also you can use it, but I'm not sure if people have been successful with CNNs on sound. But with sound, actually, even fully connected networks do pretty well. So. You can use anything. These are function classes. You can, just like you are switching between logistic regression versus LDA versus random forest, you can switch between these. But you want to kind of intuit whether it's an appropriate choice or not, at least intuition-wise, because these are very highly complex functions, so really not much statistical analysis can be done. Now, although recently people are really doing some theory for this, including in Chicago, TTI in Chicago. People have some papers recently about this, including our CS department, by the way. Okay, so this is just a graphic from some paper in 2014. It's basically saying we can get a good performance boost by just using a pre-trained CNN on several tasks. Okay, it happens to be that on images you can have object classification, scene classification, bird subcategorization, star recognition, all the way to some scene image retrieval. So very, very different types of tasks. Goals are slightly different. And they're saying instead of having previously there used to be this hand engineered features. Okay, there's something called deformable parts model, but anyway, there were some hand engineered features which would ultimately feed into an SVM, and you would do a classification or whatever is this task here. Okay, they're saying you can just download a pre-trained CNN like AlexNet or VGG16 and really get a performance boost, and they're showing performance boost. I think the green is the best and best state of the art, and CNN off the shelf is already like comparable. CNN off the shelf, so all the remaining bars are related to CNNs and they are using data. Okay. And this is just an example of what other tasks have. Like this is called image segmentation, where you are trying to exactly capture the border of that particular object. Okay, in this case, cats. Object detection, you also need a bounding box for where the cat is. Same thing with localization, I guess. And this is just a regular classification. And there are many other variations of tasks. Okay, okay, I guess the pre-trained models, you can get it from TensorFlow and Keras, which is what we're going to use in this class. Yeah, the point is, like, if you have small data, you can use either feature extraction or fine-tuning. But if it's small data and it's very different, right? If you have, let's say, medical images, X-rays, but you can't. Maybe you can, but it's not clear a priori whether you can just use ImageNet pre-trained CNN for doing something on X-rays, right? It's very different data sets. You can try, but it may not, give you anything. So this I'll try to show next time. So VGG net, it was second in the classification task in the ImageNet challenge. It has these convolution filters, value nonlinearity, 5 pooling layers, 3 fully connected layers. So this is pretty much the specification of that whole CNN which won the but came second in this ImageNet challenge. And this is a link to download the pre-trained weights and run it on your machine, except I realize it's a bit old. So Keras version and so on are kind of changing their version numbers so quickly that I don't think it works directly, the link, but we'll see. Any questions about transfer learning? Okay. So next, let's look at some training tricks, and these are really small tricks, and it's just an assortment of I think 4 tricks to help train CNNs. This pretty much that's it. That's the content for the next 20 minutes. What are those 4 tricks? The 4 tricks are, first one is about data, something called data augmentation. Quite intuitive. I'll show you what it is. And the second trick is initialization. It's not really a trick, but it's something that you need to kind of pay attention very carefully, because you're basically doing gradient descent and the loss surface is not very nice. Okay. For logistic regression, it happens to be that the loss surface, let's say 2-class classification, the loss surface happens to be nice, like a ball or something. So you really, if you do gradient descent, you will get to the best in terms of optimization, at least. But here you will not, because it looks like a valley, hills and valleys and so on. So there's another trick called batch normalization. It's just to kind of ensure that the neurons' outputs don't kind of explode or kind of become minus infinity or infinity or something like that. Don't saturate. So something related to saturation. It happens. This is an engineering trick which happens to work well. There's really no, as far as I know, there's not much theory behind it, theoretical understanding behind it. And there's another thing called dropout. Even dropout has some weak intuitive justification, but it's a way to kind of say, let me restrict the complexity of my architecture. Somehow it's doing some regularization. I'm going to describe all these 4 things in a little bit more detail in the next 20 minutes. Okay. So let's look at the simpler trick, which is data augmentation. So deep nets, because the number of parameters are a lot. If you really want to train from scratch, you need lots of data. Okay. So ImageNet really had million images just for classification, 1000 class classification. It in fact has 14 million images with 22,000 categories. Okay. People have hand labeled over a period of 10 years or whatever of this large data set, and you really need that large data set to and rich models, which is CNN is one of them, to have good performance. And of course, I mean, a couple of things, handling of data. You want to have data in terms of training. If the data is contiguous in memory, it's easy to kind of pull it out of the memory, do something, and do. That's what this point is saying. And the second point is saying you want to collect as much clean data as possible. Clean data means something which is without noise, without labeling errors and so on. Like if you give a image, 20,000 images on Mechanical Turk and ask people to label them, and you just say I'll pay you 50 cents. Maybe they'll just label arbitrarily. How there's some quality control that you want to have. So those are some issues that you need to think about. But the more technical way that we're going to look at is this, right? So we have a bunch of data sets. Data points, examples. Let's say any number. So this is our CNN, and we get the loss. What we're going to do is we're going to use a different data set. We're going to perturb the data set. Data example. We're going to perturb example xi. So from xi, I'm going to create a different example x tilde I. In the sense xi yi to something else, which I'm going to just call x tilde I yi. Okay, and then use that as a new data point. So how am I going to get? So how did I create this additional data point? So I just doubled my data set, right? By just if I knew if I've decided a function which maps from x to x tilde. What is the intuition? The intuition here is that if I have an image of a cat and the label is cat, if I maybe flip the image of the cat horizontally, on the vertical axis, it will still be a cat and it should be classified as cat. So I'm doing a transformation of the image to get a new data point. It was not originally captured, but it should also be classified as a cat. So I think there's some example. Yeah. So basically image transformations. This is an image domain. So you can do transformations like color changes or flipping or random cropping. Like if you have an image of a cat, you can randomly crop maybe 70% of the region, retain only 70% of the region. Hopefully that still has a cat. So you get many data points now. Okay. Random scaling, cropping, things like that. You can also do, so it's not just that you crop these images and you got additional data and you can just find a classifier. You can also even reuse, even at test time, given a test image, you can do these same operations, pass all these transformed images through your classifier and then aggregate the output label. Maybe you had test time, you had an image of a dog. You do all the same transformations on this dog image. You get labels. Maybe for some labels you may get cat because you cropped a region which looked like a cat's image now, but maybe majority were dogs. So you take a majority vote basically. So you can do that even at test time. So there is this. There are names for convnets, convolutional neural networks. So there's something called ResNet. Okay, it's called. It's by I think Microsoft. It won the 2015 ImageNet Challenge. Higher accuracy. So it actually, given an input image, it actually rescales the image into these resolutions and then takes it as an input. Okay. Oh, okay. At different scales and different crops. Okay, so many croppings. So it does a lot of processing and then reads the image rather than directly operate on the image. So this is a very neat trick for images. Yeah, very useful for small data sets. So it's a very simple concept. I don't know. Yeah. Yeah. This is the training part. Yeah. These tricks are to train better CNNs. So the first trick is just get more data. On the data side, what can you do? You just perturb the data and hope. With images, the perturbation is like these types of transformations, like cropping, shifting, and so on, rather than adding random noise, because random noise is gonna make the image not be a realistic image anymore. Okay. You can add noise just for robustness purposes maybe, but that would be like a measurement noise, and cameras don't really do measurement noise.
So this is what we have a small set of data, right?
Yeah. This is augmenting data, right? You are increasing your data size, so hopefully your okay, so that's on the data side. Now we're going to look at 3 tricks on the model side. Model side basically means the CNN architecture. We're really going to kind of look at something about the CNN architecture. We've already seen a few choices. The choice of the activation function, so relu versus relu versus tanh, right, versus sigmoid. And I think people converged to relu recently. I mean, actually, AlexNet was one of the first to use relu activation. People seem to prefer this one. We also, had lots of choices about how many layers, how many neurons per layer, and also, filter sizes and so on, right? There are other choices which also influence the model performance. First choice is basically just weight initialization. With what weights do I start my backdrop process, gradient descent process? Okay. So, and the other two are batch normalization and dropout. Let me just start with weight initialization. There's really no big bullet point. I'm just pointing out that weight initialization plays a key role. For example, the weights all being 0 is probably a bad idea, because if everything is 0 and if bias is also 0, all scores are going to be 0, something like that, right? And what happens is these weight values also get multiplied. So if you remember from backprop equation, backprop for feed-forward network, what happens is local gradients happen to be just the weight vectors themselves. So the local gradient of a neuron, output of the neuron with respect to its input. I did not write the output with respect to input. Will have a matrix multiplication with the local weights themselves. Okay, and if the weights are 0 or large or small, that has a significant influence on what gradients are backpropagating into the back to the previous neurons. Okay, so you can actually look at the statistics like mean and variance of the weights or functions of the weights, which are activations, to see how they influence gradients, basically. In a sense, what I'm saying is the weights initialization influences how the next weights gets generated, and they influence where you converge to. That's kind of obvious, but for really non-linear surface, loss surface L function in this neural net setting happens to be highly non-linear, so you kind of get stuck, potentially can get stuck. Okay, and there are heuristics. People have tried to figure out, okay, now since there is this issue, which weight should I start with? Is 0 a bad idea, a good idea? Is there something else that I can do? People have tried to figure out, and there are some rules of thumb, but I don't think it's very important for us. Okay. The question is whether weight should be randomly initialized then. Okay, if not 0, then you want to pick, okay, should I pick some other deterministic number, or should I randomly initialize? If I need to randomly initialize, should I sample it from uniformly random intervals between -1 to 1, or should I sample it from truncated Gaussians, or should I do something else? So people have tried to kind of try out these different choices, and empirically they have found some rules. Okay. You can look at some references later if needed. I mean, because this works, people are trying to really squeeze out as much, figure out what's the best design choices to make to have the best accuracy for at least image tasks, or this unstructured data, including text and sound, audio. Okay, the next engineering trick is something called batch normalization. So think of activation values, right? So activation values at each neuron. For every input image that you pass, you get an activation value, and the activation value also changes as training progresses because the weights change, right? So you can actually look at the activations magnitudes and their statistics, in the sense like what is the mean activation value, what is the variance of the activation value, and so on. And of course these guys get influenced by all the different choices that we made before. The reason why we want to kind of control their magnitudes, these activation magnitudes and statistics, is because again they influence gradients, because activations are also functions of W, so they also kind of, when you do backprop, your backprop, the local gradient will be a function of activation, okay, current activation value. So because they influence gradient propagation, you want to kind of control them, control activations in some sense, and people thought, okay, how can we control activations? I just have a convolution layer, a pooling layer. I can't really control activation other than what I've already chosen, like ReLU, nonlinearity, whatever other choices I've already made. So people came up with this idea called batch normalization, which tries to kind of it's like another pseudo layer in front of a convolution layer, which tries to again transform the activation value. So already I'm whatever input I get, I'm multiplying with weights, I'm passing through a nonlinearity, I got the activation. These guys are saying, okay, given the activations, let's do further another transformation. It's called batch normalization, and I'll tell you about it in the next couple of slides, to kind of control the activation magnitudes so that your training is better. Okay, again, it's an empirical technique, not much theory behind it. You should, if you have time, I don't know how much you're interested, but there is this test of time talk by I don't know, his name is Ali Rahimi. Okay, so this is a test of he got a test. Him and his co-author got a test of time award at something called NIPS. Okay, NIPS is a premier conference in machine learning where all the most recent work gets published. So they had published something in 2007, and they got an award just this last December. And in his talk, he kind of mentions batch normalization as a thing where nobody understands why it works, but it works. I mean, he's a theorist, so he wants very good intuition for why batch normalization works, but it's not the case. So if you have time, have a look at the talk. It's for general audience. Anyway, so what is batch normalization? See, the idea is to do some, because there's a name normalization, they just do some operation on the output matrix. So filter, right, on input tensor, one filter will generate one slice, right? So we're going to operate on that slice, on that matrix. Okay. Okay, that's not entirely correct. Okay. Actually, let me take that back. Yeah, so forget about the slice output tensor. So here we actually, I forgot the part batch. So here we actually have, let's say we have a million images. ImageNet has 1.4 million images, right? So let's say, and I also mentioned this word batch in batch gradient descent, where you take a bunch of data points, only take the loss value with respect to only those data points, and do a gradient update, right? Remember, there was a batched gradient descent in the first lecture. Okay, that just means that I took 10 images. On these 10 images, I am passing them forward in the CNN. Okay, I can do that. When I say I'm passing them forward together in the CNN, all I'm saying is, because there's only mostly matrix operations and so on, I can do them simultaneously for many images at the same time. Okay. If you remember, the CNN is just basically element-wise multiplication of tensors. I mean, I can have multiple tensors and do element-wise multiplication faster. Okay, and that's where GPUs shine. Now, batch normalization says, okay, I have this batch. Okay, let me look at let's say, let me look at the output of my. Let's say I have D neurons. Okay, so let's say I have an output tensor. I'm going to just make it a vector. Okay, let's say my output tensor is 10 cross 5. Okay, I had 5 filters and 10 cross 10 as the output spatial dimension. I just vectorize it. Okay, so I have 500 neurons. Now I'm going to ask what is the activation for each of my batched image. So maybe I have 10 images. So can you tell me what is the activation for each neuron for each of these 10 images? Okay. So the rows of this figure matrix is the image number, 10 images, and the columns are just the activation values of. I'm deleting the notion of tensor. I'm just vectorizing them and calling them columns, right? Now, so with this matrix, pick a neuron that's going to correspond to a column. Okay. Now I'm going to just rescale the column as this follows. So I have initially a column with like, let's call the column vector x. Okay. I'm just going to take the column vector, subtract its mean, and divide by the square root of its variance, add an offset, and I'm going to get a new column vector x hat. And I'm going to pass this column vector to future layers. It's basically trying to do some normalization across data points. Okay. Is that clear? So up till now we were not thinking about multiple data points anyway. Here there is this, somehow multiple data points are influencing each other because this offset, because this subtraction, this empirical variance computation depends on other data points, what their activation values are. Okay. And it also has some parameter here, beta and gamma. They can be again learned using backprop. So where does this batch normalization? So it's actually a pseudo layer. So it's also, you can, in terms of block diagram, it will be like a layer somewhere. So I may have an image here. Yeah. So previously we had layers like this: input, con, and then pool. You can actually, before you do the nonlinearity in the con layer, you add a batch norm operation, and then do the nonlinearity. So con layer actually had a ReLU operation at the end, right? Or ReLU or whichever nonlinearity is. Instead of, so you're basically placing batch norm in between that. So that's this. Okay. So between convolution pooling and between convolution, like the linear operation, element-wise multiplication, and the nonlinearity that you're going to use between that. Okay. So, and it's an empirical observation that it improves gradient flows, and so you can really optimize slightly better than before. Okay. So previously you may be hitting gradient values being always 0. You're not really moving in your search space of W values. So maybe with this trick you do slightly better. Okay, it's an empirical observation. Yeah, that batch. I mean, you can substitute some other numbers there potentially. I mean, the variations. There's not like a one method that everybody agrees on. Yeah, but the version I said, you can just take for that batch. Okay, the last one. I don't know how much time I have. 5 minutes. Drop out in 5 minutes. It's actually a simple idea. So let's see. So here what we're going to do is when we do a forward pass, when we do gradient update, right? When we don't do backprop, and in the training, what we're doing, we have a current set of weights. We pick a new data point, right? We pick a new data point. So this is, think of it as batch gradient descent with batch size being 1. I mean, it doesn't matter, batch size can be even 10, but for simplicity of understanding, what you're doing is you have the current weight vector, you pick one data point and find the loss value, or you can take a batch, find the loss value, and then you backward propagate the gradients, update the weights, right? But when you do this forward pass, before doing the forward pass, you delete nodes in your neural network. You delete nodes arbitrarily, like this node is deleted, this node it is deleted. In this simple two-layer network, before I do any pass, like I'll do many passes on this to get to some weight vectors, right? Eventually, that's the whole exercise of backprop and gradient descent. But in each round, in each operation, I'm just saying I'm going to delete a bunch of neurons, and which means that deleting a neuron essentially means that set its output value to 0. In the sense, it doesn't matter what the input is, output is 0 or 0. If output is 0, it's never going to influence anything else in the future. 0 is basically no influence. Delete them, and then you do backdrop, and that backdrop, of course you've deleted them, so they will not be influencing anything. Okay, so this is basically the idea of dropout. So you're dropping out a bunch of neurons while doing training. Okay, and how do you drop out? Flip a coin with some bias, maybe 0.4 or something, with 40% chance to drop every neuron. I mean, drop this neuron, try the same thing with another neuron, and so on, so forth. So that's it. That's the training procedure. Drop out. Why do you drop out is what I'll tell you now. Yeah. Okay, so the intuition, again, it's empirical intuition with some weak theory probably here and there in some papers. It's all recent techniques, so I don't know what's evolved. The intuition is that you're trying to restrict, you're trying to prevent overfitting. So dropout is like a way to regularize, as I've written here. Remember, there was a regularization which is sum of the weights squared, right? Wij, I guess. Instead of this explicit regularization, dropout is like a regularization which is trying to curtail the richness of this function. This is a function, right? It's taking an input x, outputting a score vector, right? It's a function, right? F of x is what score is. Now, dropout is implicitly trying to kind of ensure that there is some redundancy in that function. In the sense, no one node is like capturing some peculiar, specific feature. In the sense, it's trying to like keep things general. It should only capture general features. In the sense that no one node should be special or very important, roughly. So it's restricting the capability of the network intuitively. I mean, restricting the capability is obvious because if I remove the dropout nodes, then of course there are less parameters essentially. So capacity is smaller. You drop, flip coins, drop nodes, and then only do forward pass, and then update the weights of whatever you can update. Then next time again flip coins, drop some other nodes, do this. This is the engineering trick, and it's something very similar to ensembling, by the way. Because we dropped out at test time, when you pass a test image, it's like you're passing the test image over many different networks with this dropped out. Each version is like a dropped out version of the original network. It's like that. There's some interpretation like that. Okay. But it's not very important. I'm just saying that this is a trick and happens to work. I guess here is some explanation on that. So it makes us use smaller capacity of the network. Basically, neurons need not overfit to some specific idiosyncratic feature. It forces all neurons to be useful essentially. I mean, there's basically, because I'm dropping out, it's like subsampling the network and then making a prediction or something like that. It's 8:30, so let me see how many. That's it. Okay. So one last thing I wanted to tell about dropout is, I dropped out, I learned some weights, but you also need to correct for the probability that you dropped out while making a test prediction. Okay, so that small correction is as follows. Say you dropped out with probability p. Every node was dropped out with probability p in the training. Then let's say this was the function w2 times max of, it's a one hidden layer neural network. Then you have to change that to you need to add a factor of p, basically. You need to multiply your because at test time, if you're not doing any dropout anymore. At test time, you're passing the whole input and using all the neurons. So there is some rescaling that you need to do. Okay, and this is not arbitrary. I think you can show that if you drop out, like for a simple neural network, you can show that if you drop out things with probability p, then if you're not dropping out, the output is scaled by 1 by p or something, and therefore you need to have a correction factor. Okay. The parameter dropout probability p is like the lambda in explicit regularization. Is equivalent. That's it. And there was some summary. I can skip it. Okay, that's it. Any questions, you can come forward.